In this video, I'm going to introduce a visual mental model that explains not just Ethereum, but the entire crypto space, and which allows us to see why exactly this technology is so revolutionary and how we can use it to quite literally save the world. So I'm going to walk through the three major phases of computers in the internet. First, in phase one, we have regular standalone computers. Then in phase two, these computers are connected and we have the formation of a global internet, which is a bit akin to a civilizational nervous system of sorts. Then in phase three, we have the invention of the world computer. And this is a bit like the emergence of a brain at the center of that civilizational nervous system. So the central component to this model that I'm going to explain is this notion of what I call compute space. And this is a way to think about computation and what computers do in visual terms. So we imagine that every computer, whether it's a smartphone or laptop or server, we imagine every computer as generating this sort of three-dimensional abstract compute space. And this is the space where all of our applications run. So whether it's the Spotify app on your phone or the Chrome web browser on your laptop, or even the operating systems which underlie those programs, we imagine these things as running in this three-dimensional space of computation. And we imagine that these applications and programs, we imagine them as machines, as sort of abstract informational machines. And I think this is a pretty accurate, or at least useful way to think about programs, because they are mechanistic. You know, if you could somehow see a visual representation of an application like Spotify on your phone, what you would find would be this vast, huge machine, which itself is made of smaller components and smaller machines, and which these components would be transforming and manipulating data and passing them between these different modules. And the whole thing would be doing a lot of stuff, mechanistic operations, and it would be moving incredibly quickly too. And so these machines are, somewhat analogous to machines in the physical world, but these machines that we're describing here are informational machines. They operate in a realm of information. They operate on bits of information instead of atoms, of physical reality. So we're talking about an informational space, but this space, of course, like computers have a physical reality to them. So everything that happens in this imagined abstract compute space, it has an analog in the physical reality. We have some chip, some microprocessor in the computer, and within that chip there are these tiny little streams of electrons that are shuffling back and forth at, insane speeds, and gates are opening and closing and switches are switching, and that's the reality of the computer. So everything the computer does really is happening in that chip with those electrons moving around. But we project from that physical reality, we're kind of projecting like a homomorphism, like a different way to think about that process. And we're just kind of projecting it into this three-dimensional imagined space because it's, I think, easier to reason about, especially for what I'll talk about in a minute or a little bit later. It's easier to take this visual model and then understand the significance of Ethereum and the internet and so on. Now, to flesh out this model a little bit further, we can imagine that the size, the volume of any given compute space, we imagine that that corresponds to the memory of the computer, of the underlying machine. So we have this compute space and we have all of these abstract programs, these machines running inside of it, and we have a bunch of data. But the amount of machinery and data that we can fit, so to speak, in this space, that is limited by the amount of memory of the computer. So if we have a machine that has 32 gigabytes of RAM, then the total size of this compute space, the total volume of it, would be 32 gigabytes in size. And so we're imagining that the smallest unit of space, the Planck length, so to speak, of our informational little realm, would be the bit, right? That's the smallest unit of space. And so the size of the space is determined by the memory, and everything which is in the memory, everything which fits inside of this compute space, these are the machines and data which are sort of animated, they're sort of alive, they're moving, they're doing things. We can also imagine that outside of this compute space, we have an extended, wider surrounding space, and the size of that surrounding space would be determined by the disk, by the slow storage of the computer. Now, all of those things out there in this much larger, maybe 1 terabyte total size space, those things are inactive, right? They're dormant. They're flat. They're not doing anything. But if the computer sort of decides to bring those things in, it can kind of warp them in. That's what I'm showing here. The compute space can sort of reach out into the faraway regions of the disk and pull some dormant piece of machinery into the compute space and thereby bring it to life and activate it and use it to do something. And then when it's finished, it can just kind of send it back out or just evaporate it. So we imagine that the volume, the size of the space, is determined by the memory, and the size, the volume of the surrounding space, is determined by the disk speed. And then the final component is the speed at which things happen inside of this space, and that is determined by the speed of the CPU. So the speed at which your abstract machines run and transform and step through whatever they do, that would be determined by the CPU speed. And also, like if you wanted to get technical, the speed at which things move in and out of the compute space would be determined by various I/O components and memory speed and so on. But for the model that I'm going to use to explain this Ethereum and so on, we just need those 3 components. Every computer generates a compute space. The size of the space is determined by the memory. And then the wider space is determined by the disk size. And then the CPU speed determines the rate at which things change inside of that space. So a really important thing to know about these compute spaces is that they are all essentially equivalent. Every compute space is the same in a certain sense. It may have a different size and different speed at which the things run inside of it, as I mentioned. But in terms of what kind of machinery, what kind of programs you can run in one compute space versus another, they're identical. They're the same. Now, they might have different operating systems and so on and on and on, but at a fundamental level, every computer, every compute space is the same. They're equivalent. And this equivalency is this notion of Turing-Completeness and Turing machines. Quick background on Turing machines. So in the 1920s and 30s, people were building these computing machines, but this was the realm of electrical engineering. Computer science really wasn't a thing yet. And these machines were bespoke. People would build these big, complicated machines that were designed to solve some problem. And each machine was kind of a one-off. And it wasn't known yet whether there was some core fundamental essence of computation whereby you could build a machine that could then be programmed to solve whatever problem you could think of. And that changed, that was solved, that problem was answered in 1936 when Turing proposed his automatic machine, which is what he called it. So he proposed this abstract sort of model of computation, and he proved that it was general, that that thing that he imagined could compute anything that could be computed. That invention, that was like the final computer in a sense. It's like he showed that there's nothing beyond that. Like this model, this machine that he devised, it could compute anything that any conceivable machine could ever compute that we could ever imagine. Like it's the ultimate general purpose thinking machine in a sense. And maybe another way to think about this is that the Turing machine, or anything equivalent to a Turing machine, because if the Turing machine is totally general and something is equivalent to it, then it's totally general as well. These things are sort of giving us access to like a highest Platonic realm of compute space or of computation. Any machine that can take you there and reach this highest realm, it's accessing this highest realm, and there's nothing above it. And so any machine or set of rules or system which grants you access to this highest Platonic realm of computation is considered Turing complete. And it's actually not that hard to achieve Turing completeness. You can build really pretty simple machines or really simple, sets of rules, languages that achieve this Turing completeness and reach this highest level of computational, realm. So I've explained that all of these compute spaces are equivalent. They're all equally expressive. Any program, any abstract machinery that you can run inside of one compute space, you can run in any other, because they all access this highest Platonic realm of computation where they're all equivalent. Of course, modulo different amounts of memory and speed. Obviously, like one problem on a slower machine is going to take longer, and if it doesn't have enough memory, it might not be able to do it. But apart from that, they're fundamentally equivalent. These spaces are equivalent. Now, that's a bit of a lie because there are lower machines that are lower in expressibility than Turing machines. So we can imagine there are compute spaces which are strictly speaking less capable, less expressive than like this Turing space that I'm imagining here. But these lower computational kind of models, they're just really not seen much in practice. You know, like your elevator may use something akin to like a finite state machine as it's in its circuitry. So it's not a fully general computer. It doesn't partake in this kind of Turing space, compute space, whatever you want to call it. But the vast majority of computers are Turing complete, so to speak. They are as expressive as any other machine. So we imagine that they're partaking in this Platonic compute space. And one other point I'll make is that quantum computers do not actually give you access to a higher space, so to speak. Anything that a quantum computer can do, a classical computer can also do, it just takes longer. So quantum computers are fundamentally faster at certain kinds of problems, but they're just faster. It's not that they can do things you cannot do with a Turing machine. Okay, and one more thing is computers and compute spaces and Turing machines, they're general enough and expressive enough that you can actually run a compute space within a compute space. Or another way to think about it would be you can actually run a Turing machine with a Turing machine. You can have a Turing machine that is like emulating inside of it, emulating another Turing machine. And that second one is just as powerful as the first one. Like they're truly equivalent. And this ability of like nesting these compute spaces will be very relevant when I talk about the EVM in just a minute. But now we'll go on to the internet and think about how when we connect these compute spaces, what kind of new properties arise from that. Now, the things that can be done with an isolated compute space are really incredible. You can do ballistic calculations, which was one of the early use cases, spreadsheets, various other scientific calculations. You can play games. You can do a lot of things with an isolated single compute space, with a single computer. But the magic really starts to happen when you connect them, right? When you connect these compute spaces with some kind of wire, copper wire, or fiber optic, it really doesn't matter, something that can transmit information, then you have this really incredible property where the abstract machines, the programs, and the data, they can start to flow between these spaces like water. So now, instead of having your isolated compute space with your, say, 32 gigabytes of volume of space plus your disk, now you're able to access thousands of other computers, right? That's what the internet is. It's just a bunch of computers connected by information lines. And when you connect them like this, it's as if your compute space has now become like 100 million gigabytes. It's massive. In a sense, you don't quite have that, and I'll talk about that later, but in a sense, your space has just grown tremendously. And these programs and machines can zip back and forth between these computers. And this, this property has given rise to the entire modern world that we live in today, right? All of our applications and social media and internet browsing and YouTube and all of these things are the result of this simple set of properties. We have these compute spaces, which can run these abstract machines, and then they're connected by informational, like data connections, and therefore these machines and data can flow between them. And that's our modern world. Now, in the early days of the internet, we had these compute spaces connected via data connections, and it was generally a pretty peer-to-peer situation. The playing field was relatively even and flat, so to speak. You would have these computers in universities typically that would connect to each other and send data back and forth and so on. And what has happened is that model has evolved, and we now have a situation a little more like this, where we have these monolithic, huge, towering compute spaces, these huge collections of servers, and they increasingly sort of run things. And we, your phone, your laptop, etc., we are the clients, these little colonies out on the outskirts, so to speak. We sort of connect into these massive servers and have to defer kind of the running of these services and applications to those servers, right? So you can think of YouTube as something close to, something approximating the world's video library, right? It's like the global library of videos. And Wikipedia, of course, is like the global encyclopedia. And Facebook and Instagram, it's like the world's social network. And so these public, almost like public services, public goods, these are like civilizational systems. These are pretty important, pretty central systems that we use to run our civilization, increasingly used to run our civilization. And they're controlled by these monolithic, huge mega compute spaces. So the main point that I want to make about this paradigm, about this Web 2 internet, somewhat centralized paradigm, is that you can do really useful things when you have these monolithic servers. You can provide really good video services and social media services and so on. They're really powerful, but there are these limitations to them that we have no visibility into them. We have no recourse. They're the only way to achieve this shared compute space thing is by having that shared compute space run and controlled by some group, some entity. Like there's no way to, well, until now, there was no way to like make a fundamentally shared neutral compute space. You always had to have some entity who controls and owns it. So you had this fundamental limitation. And the other limitation to this paradigm is that there's certain things you cannot even do, right? If you want to make a digital money, and of course, money is like the most digital thing ever. Like computers are made to do money. If there's one thing computers can do, it's manipulate numbers, right? And that's all money is at the base level. So like money has to come to, computers have to do that task. Like it just makes a lot of sense to have a global digital money or multiple digital money systems. But you actually can't do that in this paradigm, really. The only way you can do it is that you have to have some monolithic server run and controlled by financial institutions and some government, and they can implement the money system. But again, they have complete control over it. And you can never have a global money system, right? It would be useful as a society to have a global money system of some sort, but you can't do it in this model because some entity would always have control over it. And so if like the Americans have control over that set of servers, well, half the rest of the world's not going to trust them. So like there's no way to achieve a global digital money in this paradigm unless you have a one world government, which also sits at the top of all of that, then controls the servers and so on and on and on. But like that's not a great solution. So we have this need for a truly shared neutral compute space. So the last question that I want to raise about this paradigm, and I thought about this for a long time, it's like, why at a fundamental computer science sort of level, why can't we have shared compute spaces? Like, is there some fundamental limitation there? And I think there is. The fundamental limitation is that one compute space cannot see, so to speak, into another. You know, if you're in this paradigm, you can transmit data back and forth. You can transmit programs, the machinery. These things can be transmitted back and forth, but you can't actually see. If you're inside of one of these compute spaces, if you're like living in there, you can never see into another compute space. You can see that you have some, data connection on the wall, so to speak, and you can see it blinking on and off, and you can interpret that as, you can reconstruct that data stream into like some data or some program or whatever it is. So you can like look at this little flashing thing on the wall, and like some program, some machine will kind of like pop out of that hole in the wall. So you can like transmit things back and forth, but you can never actually see really what's going on in another compute space. You have to trust, in a sense, whatever comes through that line, right? And because of that limitation, this like fundamental kind of computer science limitation to networking these compute spaces, you have to kind of revert to this model to really achieve a shared compute space or approximate a shared compute space. You have to revert to this model where we just say, okay, we're going to trust these huge monolithic compute spaces. They're going to do the computation and feed us data and feed us content and so on. And we're just going to have to trust them. And that's that. We have no recourse, really. And so this is the problem at, I think, the deepest, like kind of most fundamental level. I view this as the problem that Ethereum and any like world computer smart contract platform, this is the thing which they solve. And I'll explain how they solve it. So the first point that I want to make here is that Ethereum is a computer, right? Ethereum is a Turing-complete system. It has this Turing-complete environment, this EVM, the Ethereum virtual machine, at its center, and it is able to execute the code in smart contracts. And so what it really is, because it has this Turing-completeness, it is just another compute space. Ethereum is a computer. It's a new kind of computer, not in the sense that it achieves the accessing of some higher Platonic compute space, because that's impossible. We know that Turing machines access the highest point that you can access. But it's different in that it's this world computer. It's the first compute space which is truly shared. And, you know, this analogy of the world computer, this was the analogy that was originally used when Ethereum was developed. And it was sort of abandoned because I think people found it to be kind of confusing or vague. But it's the best analogy because it's the most accurate, right? Like, people talk about, or like we use the names now of like smart contract platform, and to me that's just a terrible name. Like, it doesn't invoke any useful analogy. Like, what is a smart contract? It's just empty. And I think it also undersells it too, right? Like, it's not about financial contracts, right? Like, it's bigger than that. Solidity is a general purpose language. It's Turing complete. The EVM is Turing complete. It's a computer. Anything a computer can do, you can do inside of the Ethereum computer in principle. Obviously, you're not going to run Doom on the EVM, but that's irrelevant. Like, the space of possible things that we will do with a world computer are vast and unknown to us, right? Smart contracts are programs. We should just call them programs, right? A smart contract platform is a world computer, and smart contracts are programs. That's it. It's a shared computer that all the other computers in the world can see into, right? They can deploy programs into this shared compute space, and they can have those programs execute. They can send data and call functions within those programs. They can, you know, as a global society, we can connect to these programs and observe them, and we can decide on which ones we want to use and coordinate under. And we have an entirely new paradigm, truly a new paradigm to networked computing. We have the emergence of this new thing, this world computer. And by the way, I said in the intro that this model would explain not just Ethereum, but the entire crypto space. The reason I said that is that because there's really only two kinds of system in the entire crypto space, at least in terms of this model that I'm describing here, in terms of the fundamental kind of computer science. I would say there's simply systems which offer a Turing-complete computational platform. That would be Ethereum, Solana, etc. And then you have systems that are fundamentally less expressive. So that would be Bitcoin, like Litecoin, like Dogecoin, I guess. These systems, they do not give us a globally shared compute space. What they give us is a globally shared ledger, right? So it's just, instead of this compute space being projected into the sky, you would just have a ledger. It's just keeping track of balances, and that's all it does. And that in itself is quite useful. Though the thing to always remember is that a globally shared compute space, it does that too, right? Like everything, you know, to bring it back to the Turing complete notion and these levels of computational machine, like a ledger is a strictly less capable computational sort of system than a Turing machine or a Turing complete system. So anything that that ledger can do can 100% be done by the world computer. And of course, the world computer can also do a whole bunch of more things, right? So in a computational, like computer science sense, you really just have world computers. That's the whole field of crypto. It's world computers and then things which do a bit less than world computers, and that would be Bitcoin, etc. Okay, so I also said that I would describe how this is achieved. How do we achieve this sort of shared compute space phenomena? And the way that this is done, and this took me a long time to figure out how to like visually represent this, like how to really get a solid handle on like what is fundamentally happening here that's different. For a while I was thinking like, okay, this world computer thing allows us to sort of see from one compute space into another. So I was imagining like a whole bunch of computers sort of arranged around this central like spherical compute space, and they had like tunnels into it or something like that. But what I realized eventually was the best way to visualize this is actually just the way that it works, right? So the way that Ethereum works is that each machine, each node, the computer, your laptop that you run at home, if you run a Ethereum node, each machine actually can see into the Ethereum compute space because it contains within it the Ethereum compute space. So a compute space cannot fundamentally ever see outside of itself. It's a different, they're different universes. They're each independent, isolated universes. They can send data back and forth and machinery and whatever, but they can't see into each other. But what you can do, and this is why I brought up virtual machines a bit earlier, nesting of these things, is that you can take your compute space and put within it this shared world computer. So now you can see into it because it's actually in your universe. It's in your domain, right? And what we do with these systems like Ethereum is all of these nodes, they do this, they run this Ethereum compute space within them. And, the ability to do that is not new. We've had virtual machines for a long time. But what has been figured out in the last, decade or so is that there's a way to take all of these machines that don't have a leader, that don't trust any central authority, we can have them cohere those nested compute spaces. So each of them runs the Ethereum client. And then we have a crypto economic way. We have these consensus mechanisms and so on. We have a way to cohere these independent sort of individual fragments of the system. They're not really fragments though, because each of them is a complete copy. Each node runs a complete copy, but then we're able to cohere them so that they stay in sync, so that these little independent computers, so to speak, they execute the same transactions in the same order. And what we get as a result of that is as these independent little compute spaces cohere, we get the emergence of this holographic world computer, right? We can, if we have to imagine like where is the Ethereum world computer, where is this compute space kind of located? Well, it's kind of everywhere and nowhere. It's contained within each of the nodes, but any one of the nodes could be destroyed and it doesn't affect the greater system. And we don't look to any single node like continuously as the leader. So this compute space is kind of projected into the ether, right? It really is like this etheric compute space that is sort of like holographically emerging from all of these constituent little parts. And so I think, when I think of like what is the best metaphor to describe Ethereum and in a sense the entire crypto space, the thing that I keep coming back to is it's like this holographic world computer that sort of is in the sky, and we can write programs into it and we can coordinate under it in just unbelievable, unknown ways that we're yet to kind of see and realize. So finally, that brings us to the transformation of that previous sort of image that I had. So in the previous paradigm, we had this monolithic server situation. We had this client-server relationship where we were quite subservient to these controllers, to these servers. And also the network topology, like if you think about in my compute space model, what we had was just a whole bunch of compute spaces that are connected to each other. Like even though the servers are very big and powerful, they're still just computers. Like in the kind of graph network theory kind of model, they're just these nodes in the network that are connected to lots of other nodes. They're clients, right? But they're no different really. Now, in this new paradigm, I think we have for the first time a sort of new node in the graph. So, like as I mentioned before, Ethereum and these other systems, they're not more powerful. They're not like more expressive than any other Turing-complete system, but they do have this different property in the network sense. In terms of our network, in terms of our internet, they are actually different because they're these transparent, auditable, like shared compute spaces, right? It's a new thing. So I've drawn this like a different looking node in this graph here. But so what I'm imagining is this previous paradigm where we have these monolithic servers evolves into something like this. Now, I think what that's going to look like is we're still going to have servers, right? It's still going to be very useful to have centralized, powerful compute spaces that do, take care of heavy duty computational tasks and so on. And especially with AI, those are things that need to be done in big, powerful, centralized servers. But what I imagine happening is that this landscape changes to where virtually every computer in the world is going to connect in some sense to the globally shared world computer, right? It might not be running a lot of computation through that system because that system is always going to be like slower than just a regular server or something. But it just seems so inevitable to me that once you have a globally shared compute space, once you have a world computer, all of your financial stuff is eventually going to go through that, right? It just makes more sense. And so at the very least, I imagine that all of these, virtually every computer in the world is going to connect into the world computer for financial purposes, right? And when I say the world computer, maybe it's Ethereum and its layer twos. I would just clump all those together as the world computer. But I imagine this is how the landscape transforms. So instead of having these monolithic servers, we still have servers, but now they're kept honest, so to speak, because they just have a lot less power. I imagine them being thinner. I imagine we may still have even kind of brick and mortar banks in like the far future where DeFi has kind of taken over. We may still have brick and mortar banks, and maybe they just supply or provide a sort of thin customer service layer on top of a bunch of open protocols. And because they don't have like deep root access to that system, they can't really screw you over. They can't really do all that much. They compete in terms of providing extra services that are valuable, right? So even in the future where we still have these servers and we still have some centralized companies and systems, the whole thing is made massively more equitable and efficient and just better because it all kind of connects into this central hub, into this nexus, like the new nexus of the internet. And again, like the analogy I used at the start of the video, I think is actually apt. We have with the internet this civilizational nervous system that is developed. We have this vast globally connected system of these computers that can kind of think sort of. They're these little, little machines. But up until now, there hasn't been any central computer. There hasn't been any central, nucleus around which that nervous system can sort of cohere or sort of develop further. And I think that's what we have now, is we have the central brain to that nervous system. So now all of these little machines, these little brains that are all connected in this nervous system kind of thing, they can plug into this central brain, and then the thing starts to behave like just a higher organism, and we can achieve, greater things as a civilization. So the last thing I'll say here is that I have this metaphor that I often use, which is the metaphor of the civilizational ship. So I imagine that our civilization, it consists of many things, but one of the classes of things that our society consists of is systems, right? We have a lot of systems and institutions that help us run our society. We have our education systems, we have our systems of government, we have our monetary and money systems and financial systems, right? We have a lot of these things in our society are just kind of mechanistic. Like we need to keep the water running, the electricity flowing, and so we have a lot of systems that do that. And these things, again, are very mechanistic. They're trying to achieve pretty straightforward goals. They're not really political. It's just like we have a lot of things that we just need to keep running. So the way that I think about that is it's like a civilizational ship. It's like we're on this great ship, and ships, when they're out at sea, they have the engine room and they have lots of logistical things that they have to do. So a lot of what the ship is doing is just keeping us out of the water. It's just trying to perform these basic functions and make sure the thing runs, make sure it doesn't sink, make sure that the lights are running, right? And, I think we're in this place in history where our civilizational ship is sort of breaking down to some degree, right? Like most of the systems and institutions that we rely on today were developed and architected before the internet, before computers, even before electricity, okay? And we're still running our whole civilization on those systems. And to me, it's pretty obvious that at this point, these things have been breaking down. And it's not just that like one set of these systems is breaking down. It's not just the universities or like some portion of the government or even the government itself. It's that like all of them are in parallel, kind of like starting to grind to a halt or become less effective, less efficient, etc. And we live in this modern world where the technology is advancing so quickly. We need fast systems. We need modern 21st century systems that are designed for this modern era. So the way that I see it is that our ship is kind of sinking, and a lot of people have noticed this over the past decades. And a lot of people are saying, we need to fix it. We need to save the ship. We need to fix this, reform this institution or this institution. But reform is really, really hard. Mark Andreessen has a tweet that I'll put up somewhere where he says, you really don't reform institutions, you build new ones. So when our entire set of institutions and systems is failing in parallel, when all of that stuff is kind of dying, you can't save the ship. A lot of people are trying to save the ship. I don't think you can save the ship. You have to build a new ship, right? So what we have to do is not just build a new money system. We have to build a new financial system. We have to build an entirely parallel financial system, money system, and ultimately, we go up that stack, we reimagine and rebuild education, journalism, media, and eventually we get to the top of the pyramid and we have to rebuild governance itself. And, to me, this is just obvious. Once you have this technology, once you have a globally shared world computer, you can start to transform these systems and institutions. A lot of that ship that I was describing, this set of these systems, that stuff can be converted to code. Maybe not entirely, but to a great degree. You can start to write programs, and you can start to use markets. You can use prediction markets to kind of like divine answers to certain questions, and you can align economic incentives so that if you do need to bring in like individual experts to weigh in on something. Maybe they have to stake a certain amount of money towards some outcome. And like I have ideas on how this would actually work. Ralph Merkle wrote a great like starter for this, I think, in his DAO Democracy paper. But I think I don't think the DAO democracy that he proposes is something we'll actually move toward. I think there's a better way to do it. I'll talk about that in another video. But my point is, when you have this technology, you obviously have to start re-engineering all of those systems that make up your ship. In fact, you need to build an entirely new ship. And in fact, we have to build an entirely new ship because our ship is sinking and the water is very cold. So, you know, not to get too biblical, but I do think of this technology as being a bit like an ark. It's an ark that we have to build. This provides us a platform, and upon that platform, we have to build the parallel society. We have to build a 21st century civilization. And if we can do that, then I think a great, beautiful, bright future awaits us. And if we can't, then not so bright. Okay, thanks for watching. If you like the diagram in this video, I will be auctioning it off on Optimism. I'm also going to be entering it into the We Love the Art contest. So if you are voting in that, please vote for me. And yeah, if you'd like to buy the NFT, there will be one edition, and I put in well over 100 hours into it, so any bids would be appreciated. I'll also be doing next videos on 4844, I think. I'd like to get that done before it actually ships. And I've been learning a lot about zero-knowledge proofs, so I may try and visually represent how zero-knowledge proofs work, which would be daunting. But anyway, yeah, thanks for watching, and I'll see you next time. Bye.